Welcome to the deep dive. So imagine trying to give a final exam to a student who has perfectly memorized, well, literally every textbook, every published scientific paper, and every recorded university lecture on Earth.
Right. You can't just ask them a harder question because they already know the answer to that, too.
Exactly. Today, we are looking at how a group of elite scientists finally figured out a way to test the, seemingly untestable. We are tracking this profound measurement crisis in artificial intelligence right now.
Yeah, it's what we call benchmark saturation. The systems are mapping the latent space of our evaluation sets so thoroughly that, frankly, our tests are losing all predictive power.
We're basically flying blind. We need a way to know if an AI is actually synthesizing new scientific thought or if it's merely regurgitating really complex patterns from its training data.
And to understand the sheer scale of this problem, we really have to look back at late 2023.
Right, when the scientific community released a benchmark called GPQA. That stood for Google Proof Q&A.
Yeah, and this was designed by PhDs to be a brutal, unyielding test. Like, if you gave it to a highly skilled human expert, they would score maybe around 70%.
But when GPT-4 took the GPQA test right after release, it scored, what, 39%?
Exactly, 39%. It decisively failed. But honestly, that failure was kind of a comforting baseline for the industry.
Oh, totally. It clearly delineated the frontier of artificial intelligence at the time. It told us mathematically that the models just lacked the architectural capacity for actual PhD-level problem solving.
But, that comfort did not last very long at all.
No, it did not. Because just 2 years later, OpenAI rolled out GPT 5.2. And that model took the exact same Google Proof test and just obliterated it, scoring 92%.
Yeah, it didn't just cross the human baseline, it totally rendered the test obsolete. Which brings us to the core mission of today's deep dive.
Right, we are exhaustively unpacking a fascinating new benchmark paper from OpenAI, authored by Miles Wang and a massive team of researchers. The paper is called FrontierScience.
And we are going to explore the meticulous, almost paranoid architecture they built to create a truly uncheatable test.
Because the creators recognized you can't just incrementally bump up the difficulty of a multiple choice test anymore. You need a complete paradigm shift.
Yeah, let's use an analogy to frame this. So imagine we built a state-of-the-art stadium to test the world's greatest high jumpers.
Okay, I like this.
We set the bar at 8 feet, then 9 feet. The athletes struggle, we measure their limits, everything works perfectly. But suddenly, the athletes walk onto the field and, well, they've learned how to fly.
Oh, wow. So raising that physical bar a few inches is totally meaningless now.
Exactly. We have to invent an entirely new sport to measure flight, and that new sport is frontier science.
That framing perfectly captures the transition. The old benchmarks relied heavily on published static knowledge, which is why they got saturated. The models just absorbed the textbooks.
Right. The new benchmark has to test the dynamic generation of novel scientific truth.
So before we get into the weeds, let's do a quick mini summary, and I want to pose a question to you listening right now. GPQA is dead. AI passed it with a 92%.
Benchmark saturation has forced us to invent a new way to measure AI reasoning.
So if you were the researcher tasked with testing an AI that has consumed the entirety of human knowledge, what exact mechanism would you build to figure out if it can actually think?
Keep that in the back of your mind, because the authors solved it by bifurcating the evaluation. They basically split frontier science into two entirely distinct testing tracks.
2 tracks requiring very different types of cognitive processing. Let's look at the first track. They call it the Olympiad track.
And the personnel they recruited to write this section is, frankly, intimidating. They brought in 42 former international medalists and national team coaches.
We are talking about people who hold a combined 108 medals from the International Physics Olympiad, the Mendeleev Chemistry Olympiad, and all those global arenas.
Yeah, and they wrote 100 gold-set questions, heavily leaning into physics and chemistry.
And the defining characteristic of this Olympiad track is its absolute demand for precise closed-form logic.
Right.
So break down closed-form logic for us. How does that practically function when you're taking a test?
Well, it means the entire complex reasoning chain must definitively resolve to a singular, undeniable destination.
Like a single correct answer.
Exactly. The model is given a highly theoretical physics scenario, right? And it has to execute perhaps 50 distinct mathematical transformations. But the final output has to be a single number.
Or a highly specific algebraic expression, I think I read. Or sometimes in biology, a fuzzy string match for a definitive term.
Yes. There's absolutely zero room for rhetorical maneuvering here.
You either successfully calculated the exact terminal velocity of that theoretical particle, or you failed. It's totally binary.
Yeah, it tests raw, constrained deductive power. It measures whether the AI can hold a complex mathematical abstraction in its memory across dozens of steps without, introducing a hallucinated variable or losing the thread.
Okay, then we have the second half of the benchmark, which is the research track. This consists of 60 goal-set questions, distributed with perfect symmetry, so 20 in physics, 20 in chemistry, and 20 in biology.
But the authorship changes completely here. Instead of Olympiad medalists, these questions were authored by 45 actively practicing PhDs, postdocs, and professors from top-tier institutions.
And the design philosophy just shifts entirely. These are not pristine theoretical brain teasers anymore.
No, they are authentic, messy subproblems extracted directly from active, unpublished laboratory research.
Which is wild. The PhDs were actually instructed to design tasks that would require a human expert working in that specific subfield 3 to 5 hours to successfully complete.
3 to 5 hours for a working PhD to solve one question. It's grueling.
But wait, let me push back on this design choice for a second because it almost seems contradictory. An Olympiad is, at its core, a really competitive exam for high school students. If the stated goal of this multi-million-dollar benchmark is to measure PhD-level scientific breakthroughs, why are we giving the AI a high school exam on one side and a grueling multi-hour post-grad exam on the other?
It's a great question. It's all about isolating different cognitive engines within the AI. And actually, we can use a mnemonic device to help cement this concept for the listeners.
Oh, I love a good mnemonic. Let's hear it.
Think of it as CORE. CORE, that stands for Closed Olympiad, Research Extended.
Okay, CORE, Closed Olympiad, Research Extended.
Right, so the Closed Olympiad tests the mechanical engine. Can the AI compute flawlessly under strict theoretical constraints? But the Research Extended track tests something much harder, which is navigating reality.
Because a genuine PhD research problem almost never resolves neatly into a pristine algebraic expression.
Never. The data is noisy, the variables interact in totally unpredictable ways.
Like a real biology problem might involve looking at a failed protein folding experiment and having to deduce which exact reagent caused the cascade failure. It requires inductive reasoning.
Exactly. The research track forces the AI to balance probabilities, exercise actual scientific judgment, and navigate deep ambiguity.
So you need the Olympiad track to prove the deductive engine works perfectly.
Yeah, and you need the research track to prove the model can actually drive that engine through the messy traffic of the real world.
That makes total sense. So to recap this architecture, we have our closed Olympiad track demanding flawless mathematical deduction, built by medalists, and our research extended track demanding messy, real-world inductive judgment built by active PhDs.
The CORE track.
Right, CORE. So knowing the nature of how language models actually work, which track do you think an AI would fail at completely? The rigid math or the open-ended reality? We'll get to those actual numbers shortly.
But building a test this hard introduces a massive logistical nightmare. I mean, if an AI has literally read the entire internet, how do you mathematically guarantee it's actually solving the problem and not just regurgitating a textbook it memorized during its training run?
This brings us to the contamination problem, which is fascinating. The pipeline for generating these questions required a draconian originality mandate.
Yeah, they were super strict about this.
Let's say a PhD author was inspired by an experiment from a published 2022 paper. They could not just copy the premise. They had to heavily modify the core parameters, swap out the chemical pathways, and entirely recontextualize the phenomena.
The whole goal is to set a trap. If the AI relies on its vast memory of that 2022 paper, it will confidently output the historical answer.
Which will be completely wrong for the newly modified parameters.
Exactly. But they took it a step further with an adversarial internal filter.
Right. While the PhDs and medalists were drafting these questions, they were actively feeding them into OpenAI's most advanced internal models. They were basically weaponizing the AI against itself.
It's a fascinating process of building an inescapable cage. If the internal AI model easily solved a drafted question, that question was instantly discarded.
Trashed. Deemed too easy to be on the frontier.
And it wasn't just a pass or fail filter, right? No, not at all. If the model scored even a 7 or an 8 out of 10 on the rubric, the human authors had to take the question back and heavily obfuscate the logic to make it significantly harder.
They only wanted questions that completely broke the current state-of-the-art systems.
And once a question finally survived that adversarial filter, it entered the verification pipeline. The scrutiny here is just critical for scientific validity.
For the Olympiad questions, every single drafted item required at least one independent review from another elite expert, followed by a holistic panel review.
But the research questions, due to their staggering complexity, required 2 independent reviews from separate domain experts.
And the rule was absolute consensus. If the author and the 2 independent reviewers disagreed on the interpretation of the biological mechanism or the math that the question was thrown out, the underlying science had to be indisputable.
Which naturally leads to the grading mechanism, which is its own beast.
Yeah, the Olympiad track is relatively straightforward to evaluate. It utilizes a deterministic equivalency checker. The script just looks to see if the AI output the exact right formula.
But you obviously can't use an equivalency checker for open-ended PhD research, so they developed a granular 10-point rubric.
Because in high-level research, the final answer is often less important than the intermediate logical steps taken to get there.
Exactly. The 10-point rubric assesses the entire reasoning chain.
So how does that actually look in practice?
Well, imagine a complex chemistry question. The rubric doesn't just ask, did it get the final yield right? It establishes rigid checkpoints, like point 1. Did the model correctly identify the primary binding affinity?
Or point 4, did the model account for the thermal degradation of the catalyst?
Right, it assigns a binary pass-fail to each discrete step of logic along the way.
But here is the paradox that really stands out to me. The research questions are deeply nuanced, evaluating these highly complex intermediate steps. But human PhDs aren't grading these test runs.
No, they aren't.
The paper states they are using GPT-5, set at a high reasoning effort configuration, to act as the primary judge model for evaluating the other models. This feels inherently circular. Aren't we just letting a hyper-advanced AI grade its own homework? How do we trust that?
It's a totally valid skepticism, and it strikes right at the heart of scaling evaluations. But we have to look at how those 10-point rubrics are actually structured.
Okay.
The researchers deliberately removed the subjective interpretation. Okay. They are not asking the GPT-5 judge model, hey, is this a well-reasoned scientific hypothesis?
Because that would be a huge hallucination risk.
Massive risk. Instead, they are asking the judge model, does the specific block of text contain this exact mathematical consideration for thermal degradation?
So they are leveraging the advanced model's language parsing ability, but binding it to rigid objective checkboxes.
Precisely. And they proved its efficacy. The paper notes that when they ran control tests comparing the model judge's scoring against actual human expert grading, the statistical variance was basically negligible. Using a highly capable model as a strict rubric checker is frankly the only mathematically viable way to run 10,000 test evaluations every time you tweak a model's weights. You just can't keep a panel of 40 PhDs on standby to hand grade every iteration.
That makes a lot of practical sense. So to quickly recap this massive logistical feat, they mandated absolute originality to break memorization. They built an adversarial filter that discarded anything the AI could already solve.
They forced everything through a consensus peer review.
Right. And they deployed an objective 10-point rubric checked by a parsed AI judge. So I throw the question to you listening. Do you trust an AI judge, bound by a strict rubric, to spot the cascading logical flaws in another AI's multi-page PhD thesis?
It really is the unavoidable future of peer review at scale, and it sets the stage perfectly for the actual performance data.
Yes. Let's analyze the evidence.
Yeah.
We will start with the closed Olympiad track, the rigorous mathematical deduction. The performance here is staggering.
It really is. GPT 5.2 currently sits at the absolute top of the leaderboard, scoring 77.1%.
That is a remarkable validation of the deductive engine. Executing multi-step, closed-form logic at an international medalist level requires immense computational precision.
And the competition is incredibly close. Gemini 3 Pro is right behind at 76.1%, and the slightly older GPT 5.1 is at 71.4%.
These systems are reliably solving problems that would break most graduate students.
But then we pivot the lens to the research extended track.
And the illusion of mastery just completely shatters. On the open-ended, messy reality of the research track, the absolute peak score across the entire industry is a tie.
Yeah. GPT 5.2 and GPT-5 both hit a hard ceiling at a mere 25.2%.
25.2%. It's a precipitous drop. They lose over 50 percentage points of competency the moment the constraints are removed.
And it gets so much worse down the leaderboard. Claude Opus 4.5 managed 17.5%. OpenAI o1 scored just 3.2%.
And GPT-4o, which was celebrated as a massive breakthrough not that long ago, scored an abysmal 0.4%. It effectively could not secure a single full point out of 100. Why is that failure so absolute?
It all comes back to the 10-point rubric we discussed. GPT-4 might start the problem perfectly correctly, but at step 3, it makes a tiny inferential error regarding a chemical interaction.
And in a closed system, it might self-correct.
Right. But in an open-ended research problem, that single error cascades. The model hallucinates the remaining 7 steps based on a flawed premise, and the rubric ruthlessly scores it a 0 for the rest of the chain.
It fundamentally proves that navigating the ambiguity of real science is a completely different cognitive skill than just doing hard math.
Absolutely.
And let's look at the subject breakdown really quick. Across all models, they consistently performed highest in chemistry, followed by biology, and they struggled the most intensely with physics on the research track.
Which makes sense, because physics at the research level often requires extreme spatial reasoning and the modeling of unseen physical interactions, which is notoriously difficult for text-based predictors.
But within this data, there is a fascinating anomaly regarding compute power. The paper explores the relationship between reasoning effort, which essentially means allocating more test time compute for the AI to process the problem, and its final score.
Generally, the standard scaling laws apply here. When they cranked GPT 5.2's reasoning effort to high, its score jumped from 18.2% to that peak of 25.2%.
Because providing more computational time allows the model to map out deeper logical trees and verify its intermediate steps.
Right. But look at the performance of the OpenAI o3 model.
Yes. When researchers increased its reasoning effort from medium to high on the research track, its score actively dropped. It performed worse.
Yeah.
How does giving a supercomputer more time to think actually make it dumber?
It is arguably the most illuminating finding in the entire benchmark. In a closed-form math problem, more time allows you to double-check your arithmetic. But in open-ended, unstructured research, excess time becomes a serious liability. The model begins to overthink.
It starts chasing ghosts in the data.
Exactly. It generates increasingly obscure hypothetical branches, inventing these overly complex biological mechanisms to explain a totally simple phenomenon.
It loses the forest for the trees.
And ends up committing to a highly improbable, deeply hallucinated solution.
It is almost comical how human that is. It literally mirrors a second-year PhD student who spends 3 weeks buried in literature reviews, completely losing sight of their original simple hypothesis because they found one weird paper from 1998.
The failure mode is highly analogous. It really suggests that raw compute is not a silver bullet for scientific discovery. The AI fundamentally lacks an internal mechanism for knowing when to just stop ideating and commit to the most elegant solution.
So to summarize this dramatic disparity, models easily clear 75% on impossible math, but completely hit a wall at 25% on messy research tasks. And giving them more time to think sometimes sends them spiraling down dead-end rabbit holes.
Yeah.
So with state-of-the-art AI only grasping 1/4 of real-world research logic, how does this alter the timeline for when we might see an AI autonomously winning a Nobel Prize?
I think it forces a massive recalibration of expectations. The 25% ceiling indicates we are still missing a fundamental architectural component required for true scientific intuition.
Which naturally transitions us into discussing the profound limitations of this benchmark, which, to their credit, the authors themselves are incredibly transparent about. They outline 4 distinct boundaries. Let's look at the first, constrained ideation.
Right, so the FrontierScience benchmark presents the AI with a pre-packaged, highly defined subtask, like solve this specific protein failure. But the essence of brilliant science is often the ideation itself.
Right. An AI can crunch the data you give it, but it doesn't walk through a forest, notice a strange fungus, and ask, I wonder why that species is surviving the drought.
Exactly. It lacks the generative curiosity that sparks the scientific method. The second limitation involves rubric reliability. We established that the AI judge model is highly effective and objective.
But the authors concede that measuring open-ended text can never be as flawlessly deterministic as checking a mathematical output.
Right. There remains a microscopic margin of interpretive error that could skew results at a massive scale.
And the third limitation is perhaps the most existential. It's the text-only modality of the benchmark. Real science does not exist entirely inside text files on a server. It is intensely physical.
This is the classic brain in a vat problem. The benchmark tests theoretical prowess, but actual biology requires wet labs, pipetting precise microliters of fluid and cultivating petri dishes without contamination.
Physics requires physically calibrating intricate laser arrays. You can have a 100% perfect hypothesis, but if your hand shakes while pouring the reagent, the experiment is dead.
Exactly. This benchmark completely ignores the massive physical and operational intuition required to execute science.
And finally, the fourth limitation: no human baseline. This really stood out to me. They know these questions take working PhDs 3 to 5 hours to write and solve.
But they haven't yet run a statistically significant control group of actual human scientists through this exact 60-question research gauntlet under test conditions.
They plan to establish that baseline in future iterations, but currently, we only know that GP 5.2 scores 25% against the absolute ideal answer.
We simply do not know if the average exhausted postdoc would score 40% or an 85% under the exact same rigid rubric.
Right. So let's synthesize all of this into a cohesive picture of where we actually stand today. The old multiple choice tests are dead. AI memorized them.
GPQA is obsolete.
So we built FrontierScience, split into the C or E tracks.
Yeah.
The mathematically precise closed Olympiad, and the messy, open-ended research extended track. We force the models through an adversarial anti-contamination filter and judge them against a granular 10-point rubric to prevent hallucination.
And the data revealed a very stark dichotomy. The models exhibit phenomenal deductive stamina, easily clearing 77% on the math-heavy Olympiad track.
But they fundamentally fracture when faced with inductive, open-ended reality, maxing out at a 25% ceiling on the research track, often overthinking themselves into oblivion when given too much compute.
Ultimately, the current frontier models are brilliant, tireless, but entirely desk-bound theoretical assistants.
They can solve the impossible chalk equations you leave on the board overnight, but they cannot physically set up the lab, and they lack the curiosity to decide which experiment is actually worth running tomorrow.
They possess the computational power, but they still lack the physical interaction and spontaneous ideation that really defines human discovery.
Which leaves us with a final provocative thought for you to ponder long after this deep dive ends. Let's assume we solve the architectural limits. Fast forward a few years, and an AI finally masters this benchmark, scoring a flawless 100% on the research track.
Generating perfect, Nobel-worthy hypotheses.
Right, but it is still just software. It physically cannot hold a pipette or look through a microscope. When that day comes, who is actually doing the science? Is it the human technician executing the manual labor, or the AI generating the genius? Let us know what you think.
It's a paradigm shift that will force us to completely redefine the word scientist.
Thanks for joining us on this deep dive. We'll see you next time.